So today we're going to start a discussion of chapters 8, 9, and 11. This is a term that I don't know if the book actually uses it, but it is a really common term in the medical, psychiatric, psychological world. We call these functions vegetative functions. These are basically like the body's maintenance functions, and they include sleep and eating in particular. And for instance, in depression, it's really common to talk about the vegetative pattern of depression, and there's a so-called typical depression where people have hypophagia and hyposomnia, meaning they eat less and sleep less. And there's also an atypical depression where people have hypersomnia and hyperphagia, where they eat more and sleep more. And as it actually turns out, atypical depression is not particularly less common than typical depression, so the name is kind of a misnomer. But that pattern in the atypical depression is called a reverse vegetative pattern, because there's a hyper and hyper rather than hypo and hypo. But conceptually, there's a lot of sense in linking these three chapters together because the things that chapters 8, 9, and 11 talk about have common mechanical underpinnings, like common neurotransmitters, like the large peptides. We'll be talking about leptin, which was in the discussion today, and also again when we talk about eating. We'll be talking about some of the neuronal peptide Y in multiple contexts. So there are common chemical underpinnings. Orexin is another one that affects multiple things within this world that I'm calling vegetative functions. That is what is in chapters 8, 9, and 11 of the book. So let me talk about sleep today, though. Let's talk about sleep. So first of all, I want to offer the idea that sleep can be thought of as a behavior, although a lot of times you might kind of casually think of sleep as the absence of behavior. Sleep can be considered a behavior. It's something that people do. Sleep is a behavior that can be characterized. And it can be characterized by gross behavioral variables and by more subtle electrophysiological variables. On the behavioral end, you can do things like measure how long it takes a person to get to sleep and when they try to go to sleep. So when your bedtime is and when your sleep onset is. You can measure how many awakenings they have in the middle of the night, how long those awakenings are. You can determine when they finally wake up. And between these three, you can figure out how much they actually slept. You can also look at how their sleeping behaviors during the day. Are they falling asleep during the day when they want to? Are they taking naps? Are they falling asleep during the day when they don't want to, like in the middle of a conversation or a movie or while driving? So those are all behavioral variables, right? Like you can go home and measure all of these things about yourself or your brother or your partner or whatever. There are also things that you can't just go home and easily measure for yourself, like muscle movements, eye movements, electrical brain activity. When I say electrophysiological, what I mean is you're using an electrical monitoring technique, like EEG, to measure a physiological piece of data, like brainwaves. The electromyogram, that's just an electrical measurement of muscle movement. The electrooculogram is some electrical measurement of eye movement. And the EEG, electroencephalogram, is just an electrical measurement of brain activity. So these are also potentially useful. And there actually recently has been a lot of interest in doing some of this at home. You can actually buy an EEG for less than, I think, $300. Really simple one. You're probably not going to sleep in EEG at home. But there's a thing called actigraphy, if you've heard of it. You can wear a wristband that can track data like how active you are physically during sleep. And actually pretty accurately tell you what's happening while you're sleeping. I guess you could conceptually also put a video camera in your room. But there are ways you could track this at home if you wanted to and learn something about yourself. And there are actually apps in iOS and Android that will help you track this data and make sense of it. I think the way those apps work right now, a lot of them you have to sleep with your iPhone, which seems kind of ridiculous. But there are some that interface with these actigraphy bands, which usually worn like wristwatches. So it is possible that you can figure out some patterns in your sleep, and maybe someday even handle insomnia behaviorally without needing a specialist to help you do it. So I want to talk to you about some of these measurements that you can make that tell you more about what is happening with sleep. In particular, I want to talk to you about EEG. So electroencephalograms, I showed you some examples of brain patterns. Again, the EEG is measuring electrical activity from the brain. There are some good things about it. It's cheap, it's easy to do, it's fast, the time resolution is very good. The bad thing about it is there's something called a space charge effect, which means that if you're measuring the electrical field outside of a conductive body, like the head, you can only tell what the surface currents are. You can't do any depth penetrating measurements. And that's the reason that EEGs don't directly correlate with what's going on in specific brain structures. The magnetic field doesn't have this limitation for reasons that have more to do with you're going to talk more about in your physics class than in your psychology class. But magnetic field doesn't have this limitation, and magnetoencephalography can do three-dimensional resolution inside the brain, but EEG really cannot. But these overlying scalp electrical currents can be correlated with brain activity in meaningful ways. And I want to introduce you to some ways that we measure electrical activity in the brain. So, the big thing that you look for in EEG is wave patterns. We've been talking about waves for weeks now. Their frequencies and amplitudes and so forth. And frequency is going to be an important variable here again. These are low frequencies compared to some other things, like the frequency of light, or even of sound. Like just as comparison, sounds are in the 20 to 20,000 hertz kind of range, and here we're talking about 8 to 10 hertz, right? So these are relatively low frequencies. So first of all, let me introduce some basic electrical states, and I'll show you pictures of these, which are also in your book. The alpha electrical state is a 8 to 12 hertz pattern, so about 10 times a second. And this is something that you have when you're awake. And in particular, it's easily visible if you're relaxed with your eyes closed. The more you're thinking, if you're trying to solve a problem, you won't see a lot of alpha activity. But if you're just relaxing, if you're not trying to use your brain, you'll see alpha activation. Beta activation is an irregular low amplitude wave. It's not as regular, but it does have frequencies around 13 to 30 hertz. What's different about beta and alpha, in addition to the frequency, is that relaxed alpha is synchronized. It's happening at the same pattern in multiple parts of the brain. Beta is desynchronized. Different parts of the brain are doing different things. And that can be due to active cognitive processing. It doesn't make sense for your brain to process information by all the parts of your brain doing the same thing at the same time, right? We've already talked about the idea that the brain has localized information processing systems, like Broca's area. And so beta activity is not synchronized. With that introduction, those are waking EEG activities. Let's talk about what EEG looks like in sleep. There are 4 stages to sleep that I want to review briefly. The first stage is stage 1, and it lasts about 10 minutes from the time that you fall asleep. And the activity is called theta activity. Lots of Greek letters. So theta is synchronized neocortical firing at this frequency, about 5-6 hertz, somewhere between 3.5 and 7.5. And this really serves as a transition between waking and sleeping. And actually later we'll be talking about some unique things that can happen during that transition, like hypnagogic hallucinations. That lasts about 10 minutes, and then you enter into stage 2 sleep. Stage 2 sleep lasts for about 15 minutes, and theta activity continues, but then there are some new things. Sleep spindles, which are bursts of activity. 2 to 5 times a minute, you'll see these 12 to 14 hertz bursts. So they're not continuously happening, but they're just happening a couple times a minute. And then K complexes, which are sudden sharp waves that are only seen in stage 2 sleep, and they inhibit waking. So what these K complexes seem to do is, normally you hear a sound and it alerts you. That's what your brain is supposed to do. It inhibits the alerting effect of that external stimuli. So that external sound has to be really loud to wake you up, whereas normally it'll be quiet. People who wake very easily, who don't need much to wake them up, they may have abnormal K complexes. Is there another strange bug in there? Great. So K complexes may keep you asleep, essentially. Stage 3. Stage 3 sleep, then, is the first slow wave sleep. And stage 4 is also slow wave. These waves are less than 3.5 hertz. So in comparison, this activity was faster during stage 1 and 2. Now the waves are very slow, 3.5 hertz. Compare that to 8 to 12 hertz. So this is 3 or 4 or 5 times as fast as stage 3 sleep. And that is called delta activity. And in stage 3, there's 20 to 50% delta activity. And then in stage 4, the delta activity becomes even more prominent. It becomes a majority. Stage 4 also contains REM sleep, which usually happens about 45 minutes after stage 4 starts, or about 90 minutes after you fall asleep. And REM sleep, you probably have heard of before. REM sleep is desynchronized, like beta activity, which was due to active cognitive processing. REM is also desynchronized. And there is theta activity, which you see when you're awake, and there's increased cerebral blood flow, meaning more blood is available to the brain, meaning the brain is using more energy. There's also eye movements, which are normally not really present in other aspects of sleep. Interestingly, the eyes are moving, but the rest of the body is paralyzed. So there's a profound reduction in the rest of the motor activity by design. And then finally, there's sexual activation. And as the book mentions, that's not necessarily linked to sexual dream content. So that's just a part of REM sleep that's normal. Thereafter, so by sexual activation, I mean erection in men and vaginal secretions in women. So that happens as part of this. And after this initial bout of REM sleep, your sleep alternates between REM and non-REM sleep. And initially, it's mostly stage 3 and 4 when it's not REM sleep, and then later it's stage 2 and REM sleep. It goes in 90-minute cycles, and about 20 or 30 minutes of REM per cycle in normal, stable sleep. Here are pictures of that. And so here is that 8 to 12 hertz alpha activity. Here's the beta activity at the higher frequencies. I think that was right. 13 to 30 hertz. Notice how, well, it's kind of hard to see in this picture, but the alpha is a little bit more regular if you did a frequency spectrum, more regular than the beta activity, and also synchronized, which you're not seeing in this picture. And then the stages of sleep. Stage 1 has a theta activity. In stage 2, you're adding sleep spindles and K complexes. In stage 3, you're adding delta activity. See, there's not much of it, but it's there. And stage 4 is a lot of delta activity. And then REM sleep, notice, looks a lot more like being awake than it does like sleep. So this is graphically what that looks like over time, like during an 8-hour night of sleep. You start in stage, see how to explain this. You start in stage 1, and you move into stage 4, and this one is waking. So you're awake, then you're in stage 1, then 2, then 3, then 4, and then you have REM sleep, and then you fall back into stage 4, and you have REM sleep, and you fall back into stage 3. You have REM sleep, you fall back into stage 3, and then later in the night you have REM sleep, and you fall back into stage 2, and so forth. And then ultimately you wake up again. So the REM sleep is distributed over the course of the night. It becomes more frequent, and it can also be adjusted depending on the quality of your sleep. But that's what sleep looks like structurally. So that's normal sleep. And what I want to do is present this to contrast it with abnormal sleep. I'll mention briefly too that there's normal variation in sleep. There are people who can sleep 5 hours a night and be refreshed. There's some people who need 9 or 10 hours of sleep per night in order to feel refreshed. So you each have a set point. And generally speaking, your set point is going to be when you can pretty consistently feel refreshed in the morning and when you're not falling asleep during the day, right? That's the amount of sleep that you need. Also, the amount of sleep changes over the lifespan. Infants sleep a lot, and then sleep tapers down over the course of childhood to the adult levels in adolescence. But even teenagers need more sleep than adults do. And we emphasize that sometimes, that they need a little more sleep. And people sometimes, especially during the teenage years, if you remember back to high school, there's often a lot of pressure to cut back on sleep in order to get everything done. There's probably a lot of pressure to cut back on sleep now in order to get everything done. But your normal level as an adult, most of you is probably in the order of 6 to 8 hours, something like that. Normal sleep onset is on the order of 10 to 30 minutes. Some people fall asleep faster than that. If it's consistently more than that, that's unusual. The number of awakenings that happen over the course of the night also changes over the course of lifespan. Most of you are probably in your late teens or early 20s, right? At your phase in life, sleeping through the night is pretty normal. But even in your 30s, it becomes fairly common to wake up a couple times in the night. The difference between insomnia and normal sleep is that you should be falling back asleep pretty easily most of the time when you wake up. That's normal in your 30s and 40s to wake up a couple times, be awake for a few minutes and fall right back asleep. If you're up for 2 hours, that's abnormal. So all of that is normal variability in sleep. Later I'll mention some sleep disorders. There are also some normal variants in childhood sleep, like sleepwalking is not that unusual. Sleep talking is not that unusual. Most of the time it goes away. It's not problematic. Night terrors, similarly, normal sleep variations. So any questions about normal sleep? All right, let's talk about abnormal sleep. Insomnia affects 25% of the population occasionally and at least 9% regularly. And some estimates peg the diagnosable sleep disorders, the one that meet clinical criteria, as many as 50 to 70 million Americans out of, like 350 million Americans. A lot. It needs to be taken again into the context of normal variation in sleep. And so you have to look at things like, is sleep restorative? And are you talking about occasional bad nights of sleep that are reliably precipitated? Like you get a bad night of sleep on Saturday because, Saturday morning because you were out late partying on Friday night, you drank a lot, right? That's not necessarily a sleep disorder because if you didn't drink Friday night, you'd have a normal night's sleep. So are there known factors that are causing it, or does it take on a life of its own? So it's called primary insomnia if the insomnia is the core problem. And primary insomnia consists of difficulty initiating sleep, maintaining sleep, and or non-restorative sleep. Meaning that you don't feel refreshed in the morning and ready to go. You can feel groggy for a little bit. Again, that's normal. Lots of people feel groggy for 5-10 minutes. But if you're still groggy, say, like after you get up and take a shower, you still feel groggy, that's unusual. Clinical insomnia is defined as having this more than 3 times a week for more than a month. Although some people will treat insomnia, acute insomnia that is less than a month long. And all clinical criteria of this kind are defined by distress and impairment. There has to be some kind of effect of not sleeping. It's called primary insomnia if another disorder doesn't cause it. So if it's not part of another specific sleep disorder, or, which I'll tell you about a few of those, if it's not due to a substance or a medical condition, GMC, general medical condition, sorry, that's primary insomnia. And so another way of saying that is that primary insomnia is essentially when tension, body tension, and learned behaviors that are incompatible with good sleep play a predominant role in the maintenance of poor sleep. Most people think of primary insomnia as a highly behavioral disorder. People with insomnia might be apprehensive or concerned about their sleeping. And you are familiar with that. Like, you can worry so much about creating a positive impression with somebody you made at a party that you look like a freak because you're so nervous, right? You can worry so much about doing well on a test that you spend all your time worrying instead of studying, and you do poorly on the test or you blank out during the test. You can worry so much about falling asleep that it keeps you up all night, right? So that's not good. And maladaptive sleep preventing behaviors. That could be drinking alcohol to fall asleep, but the alcohol tapers off in the middle of the night and wakes you up. It could be sleeping a lot during the day because you didn't sleep at night, but the fact that you slept during the day then causes you to not feel sleepy at night. The next night, you have another bad night's sleep and it becomes self-maintaining. Your sleep fragments. In insomnia, we talk about this triple P model of chronicity. And this kind of relates back to what I was talking about with obesity. Everyone has some level of predisposing risk. You're predisposing risk to obesity and similarly to insomnia. So some people are very likely to develop a sleep disorder. Some people are relatively very unlikely. They're good sleepers. You know, like you can do almost anything and they'll sleep normally. So some people have high predisposing risk and some people have low predisposing risk. Insomnia occurs due to some precipitating event. Maybe that's a life stressor, like you have lots of work and so you're staying up late studying. Or you have a friend who's going through a crisis and they call you at 11 o'clock every night and talk to you for 2 hours. Or you party a lot and so you're up late. Or it could be a wide variety of life stressors. It could be a precipitating medical event, like you're in pain and so you're not able to fall asleep, or your stomach hurts, or you're throwing up or something like that. That predisposing event is usually transient. It's not permanent. You have pain, but that pain goes away. The problem is that the sleep disorder that it created doesn't go away. And that's the perpetuating part. And so the model of insomnia is that everyone starts out with risk. Then something triggers the insomnia. But then the insomnia takes on a life of its own and continues after that thing that triggered it goes away. And you can apply this kind of model to lots of disorders. Like, everyone has a risk of depression. Based on your risk level, you may need more or less stress to become depressed. But you could become depressed if you have a sufficiently strong life stressor. But then, not everyone becomes depressed. Like that life stressor happens and you feel down on yourself, but then it goes away. Depression is when it doesn't go away, it perpetuates. And so in a similar kind of fashion, it becomes chronic and it takes on a life of its own. It has its own mechanism that perpetuates it, but it's not the mechanism that started it. So in chronic insomnia, for instance, you stop partying, but you're still not sleeping well. Or it's the summer, and you no longer have to stay up studying, but your sleep doesn't improve. There are also secondary or comorbid insomnia. And so, for instance, depression is commonly associated with changes in sleep. The idea of secondary insomnia would be that if the original condition goes away, then the insomnia also goes away. So this is a medical condition, but say like your insomnia was secondary to having too much studying to do. It should go away as soon as the term is over, right? Like you should sleep well during Christmas break. You should sleep well over the summer. Otherwise, it's probably not secondary. Similarly, if you treat the depression and your mood gets better and you go back to sleeping well, you can make a strong argument that this sleep problem was secondary to the depression. But it can also be comorbidity, where it's not fully true that treating something else will make the sleep problem go away. It's actually multiple problems that you have. And some people, you treat their depression and it goes away, but they're still not sleeping well. And this is just a side note, but middle insomnia, which means waking up in the middle of the night, as opposed to early insomnia, which means having trouble falling asleep, or late insomnia, which means that your sleep night ends too early, like you're supposed to wake up at 7, but you wake up at 5. Middle insomnia means you're waking up at 1 in the morning and then you're having a hard time falling back asleep, or 2 in the morning, or 3 in the morning. That's middle insomnia. That's more common in these people who have multiple, more comorbid medical problems. I want to briefly mention other sleep disturbances. So I mentioned that insomnia was called primary insomnia and it was not caused by another specific sleep disorder. So what did I mean by that? These are some specific sleep disorders. Obstructive sleep apnea. Obstructive sleep apnea means that your windpipe is being obstructed during sleep. And I think that's just a fly. Obstructive sleep apnea is most commonly caused by being overweight or obese, although that's not the only cause of OSA. People who sleep on their backs generally have more significant OSA. People who have high blood pressure are more likely to have this. In little kids, it can commonly be treated by taking the tonsils and adenoids out. Sometimes you can use a dental appliance that'll hold the throat open. Sometimes you can behaviorally teach yourself to sleep on your belly or your side instead of your back. And then CPAP, which basically is a machine that blows air into your lungs. So that basically it keeps your windpipe open by keeping air in your windpipe. That's obstructive sleep apnea. So generally speaking, like the classical obstructive sleep apnea picture is, you ask them if they're sleeping well at night, they tell you to sleep just fine. But what's not so good is that they're falling asleep when they don't want to during the day. Like they watch a TV show, they're sleeping. And maybe even worse, they're sleeping in the middle of conversations or sleeping while they're driving. And that happens even when they get what they perceive to be a good night's sleep. You can also have insomnia alongside sleep apnea, but the more classical picture is that you're perceiving yourself as sleeping well, but you're highly somnolent during the daytime. There is another kind of sleep apnea called central sleep apnea. It's called obstructive when the windpipe gets obstructed. It's called central when the nervous system is causing it. It's a brain disorder. It's less than 5%, of sleep apnea cases. It's harder to treat than obstructive sleep apnea. The book talks about narcolepsy in more detail. Narcolepsy means that you have multiple daily episodes of extreme drowsiness followed by sleep attacks. What's different from this is that it's not necessarily correlated with sedentary activities. Like the more sedentary the activity is, the more likely you are to fall asleep in general. And then that gets cranked up with sleep apnea. Like if it's a boring TV show, you're gonna fall asleep, or a boring conversation. Narcolepsy can happen even when that's not true. So it can cause cataplexy, or inappropriate triggering of muscle paralysis outside of REM sleep. So you're talking about how the muscles get paralyzed during REM sleep. Otherwise, the muscles ought not to be paralyzed. That makes you fall over. That's cataplexy. It can also include the opposite, which is an extension of REM sleep into waking. So this is the extension of the muscle inactivation into waking, and this is the extension of the cognitive part of REM sleep. Sorry, let me say that carefully. So this is, cataplexy is when you suddenly have muscle paralysis and you're not in REM sleeping. You can also have, I don't think this slide makes sense, you can also have the opposite. You can also have other aspects of REM that intrude into waking hours. And then I want to briefly mention that there are some other sleep disturbances that are movement disorders, like restless legs and periodical movement. So there are disorders of motor activity during sleep that should not be there. There are some other ones that I didn't mention here. So there are certain kinds of epilepsies where the seizures occur only while sleeping. And there's actually an interesting kind of epilepsy-related disorder where not only do you have abnormal activity during your sleep, but it's actually continuous. And there's a rare condition called Landau-Kleffner syndrome where you have continuous abnormal electrical activity in your language cortex. And what it causes is, starting around 4 or 5 years old, you have a dramatic loss of your language skills, both your speaking and your understanding. It actually can be confused with autism. What's different from autism is that these kids can non-verbally communicate just fine, and also they had normal development up until 4 of their language skills. That's Landau-Kleffner syndrome. That's an electrical abnormality in sleep. So these are all sleep disturbances other than insomnia. Briefly, I'll mention the Epworth Sleepiness Scale. These are situations that elicit the somnolence that happens in obstructive sleep apnea. High scores on this are suspicious for sleep apnea, especially if they happen even when you get a good night's sleep. Briefly, I want to mention hypnagogic and hypnopompic hallucinations. The book may only mention this word. So the difference is just whether it happens during the onset of sleep or the resolution of sleep. I think the hypnagogic is the onset of sleep, and the hypnopompic is the resolution of sleep. So this happens when you're falling asleep, this happens when you're waking up. And basically what they have to do is intrusion of REM activation into the waking world. So a hypnagogic hallucination, you're falling asleep and you're having REM sleep while you're falling asleep, so you're awake but you're dreaming, essentially. And so it causes you to hallucinate. It can be relatively innocuous. You can just sort of feel like you're dreaming but also awake. You have a mixture of the two. It can be also serious. The book talks about the case where the person was having these dreams that their roommate was trying to kill them during their hypnagogic hallucination.
Is that where the feeling of feeling like you're falling and then jumping comes from? You know, you're feeling like when you're, because it
Yeah.
when
So
I
like you're
think of
falling,
it
so you're-
happen, yeah.
Yeah.
Or like you kind of are dreaming that you're falling and then all of a sudden you jerk yourself awake.
Maybe. Generally speaking, you don't have REM activation right when you're falling asleep, but sometimes you can. And that can happen. Like sometimes when you're doing that, you also have the dream experience.
Yeah.
That particular thing may also be more an issue that you have. So we talked about those K complexes that keep you asleep, right? You have alertness mechanisms, right? Like we talked about how your body maintains postural tone. So as you're falling asleep, that process is tapering off. So that, because you don't want to maintain postural tone while you're sleeping. Humans don't sleep standing up. What could also be happening is that as that tapers off, you need a larger and larger postural abnormality to alert yourself. Like normally just a small change in your posture, you quickly correct and you don't even notice it. What may be happening there is a larger change in your posture like this, and then you're correcting at that larger one. Just like a loud sound will still wake you up when you're sleeping. Maybe more of that. Because the same thing happens sometimes when you're not breathing. It's a good question. So these can be normal, or they can also be associated with narcolepsy. Again, both the intrusion of REM into waking in the sense of the cognitive activation, like the hallucinations, or the body paralysis. So, I mentioned this chemical orexin, which we'll be talking about again when we get to eating. Orexin is related to narcolepsy as well. And as it turns out, there are two kinds of orexin receptors. And the B receptors have more to do with sleep, and the A receptors have more to do with eating. So we'll talk more about orexin next time. Knocking this receptor out in animals will cause narcolepsy, this orexin B receptor. However, in humans, it appears not so much that they're born without these receptors, but they're intact at birth and they get destroyed, apparently due to an autoimmune process, meaning the body is attacking itself. In this case, it's attacking the orexin receptors. Another example of an autoimmune process is type 1 diabetes, where the body is attacking these cells that produce insulin. And that process happens in adolescence, and then later you get narcolepsy. Possibly there's a common explanation that explains why this process doesn't start before adolescence. We talked about BDNF, maybe, I don't know if that's related to this or not, but maybe there's a similar process that keeps this at bay until adolescence.
When I worked at Helen DeVos Children's Hospital, I had a 2-year-old who had narcolepsy, and they were doing a lot of studies on him because that's really abnormal for kids to have it.
So it can happen, but it's very uncommon, yeah. And it's potentially really interesting, because if you figure out why that 2-year-old got it, whereas most of them don't get it that early, it might teach you something about
Well, because his mom and his grandma had it, but they
Okay.
both didn't get it till they were older.
Oh, interesting.
So, which is interesting.
Yeah. Sometimes with those kinds of patterns, it gets progressively younger. Like that can happen with Huntington's disease. The more copies of the Huntington's variant you get, the earlier the disease happens and the more severe it is. And the copies increase over time. And so in families with Huntington's, the disease can get earlier and earlier. That happens with some other hereditary diseases. I don't know if it's relevant to narcolepsy or not. Interesting. There are medications available for narcolepsy. They don't particularly work on this orexin B receptor. They work on other things. So that's narcolepsy, which again is a disorder where you have sudden sleep, sudden drowsiness. REM sleep behavior disorder is kind of the opposite. So in narcolepsy, REM intrudes into waking, in the waking day. In REM sleep behavior disorder, waking neurological functions intrude into REM sleep. So in narcolepsy, you could be paralyzed when you were not supposed to be because you were not having REM sleep. In REM sleep behavior disorder, you have a failure of muscle paralysis to happen during REM sleep. So you're acting out your dreams. It can occur in isolation, but more commonly part of a neurodegenerative disorder. It can be an early hallmark of Parkinson's disease and some other related disorders. And it can be treated with benzodiazepines as it happens. We're not going to get into why that is the case. But here, so the common link between this and narcolepsy is that it's a blurring of the line between sleeping and waking. In narcolepsy, you have things that are only supposed to happen when you're asleep and are happening while you're awake. In REM sleep behavior disorder, you have stuff that's only supposed to happen while you're awake, happening during your sleep. There are also some slow wave sleep disorders. We talked about, remember, stage 3 and 4 are slow wave sleep. Enuresis, for instance, wetting the bed, is a slow wave sleep disorder. It primarily happens during stage 3 and 4 sleep. Somnambulation, sleepwalking, night terrors. Night terrors have physical manifestations that look like fear responses, but there's no dream that's happening. So it's not that you're responding to a scary dream, it's just that you're having these physical manifestations of fear response. We talked about in the fear lecture, the emotions lecture, we talked about how those types of responses, the behavioral, autonomic, and hormonal responses can be differentiated, can be dissociated, and you can have, here you're having just a behavioral response of fear. So enuresis can actually usually be managed behaviorally. The behavioral management for enuresis involves basically a device that detects small amounts of moisture and wakes you up right away. It's classical conditioning that teaches you to wake up. I mentioned briefly in the classical conditioning part of a previous discussion that you can classically condition behaviors during sleep. Here's an example of that. Another example of conditioning during sleep is in a sleep apnea treatment. You can sew a tennis ball into the back of your pajama top. And when you do that, and when you sleep on your back, it hurts because the tennis ball is there. So you roll over onto your side or your belly. You can teach yourself, then later you can remove the tennis ball and still sleep on your side or belly. So you're teaching yourself via conditioning even though you're not awake. And that's consistent with the fact that the cortex is not really involved in conditioned learning. So we've mentioned night terrors. These are things you usually grow out of. Enuresis is considered abnormal after about 5 years of age. It's more common before that. But for the most part, you grow out of these. If they don't go away, they can be clinically significant. There is also another one that I want to mention briefly, which is sleep-related eating disorder. It's an unusual behavior to wake up in the middle of the night and eat food. And there are actually 2 different kinds of nighttime eating. One of them is that you actually wake up and eat, and the other one is sleepwalking that involves eating, where you're not awake and you're eating. And they have different mechanisms. Both of them are uncommon though. Generally speaking, it's not uncommon necessarily to be thirsty in the middle of the night, especially if it's hot or dry. And so sometimes you wake up and drink water. That's fairly normal. Waking up and being hungry is abnormal if it happens before the morning. So let's talk just briefly about why we sleep. So sleep, first of all, you should know is a broad behavior that occurs in many different kinds of animals. All mammals and birds sleep, and at least some aspects of sleep are present in fish and amphibians and reptiles. So it goes back quite a long way. All the vertebrates sleep. And it seems that the slow wave sleep functions to allow the brain to rest. And that's consistent with the fact that their cortical activity is not very high during slow wave sleep. Interestingly, some animals actually have adapted themselves so that they sleep one half of the brain at a time. Remember we talked about the WADA? That's a test where you put half the brain to sleep on purpose to see what the other half of the brain can do. These animals can actually do that to themselves, and they actually sleep with one eye open. So the eye that is contralateral right? Because that contralateral eye is being controlled by that side of the brain, right side of the brain, left eye, left side of the brain, right eye. So the contralateral eye is monitoring for threats, while the ipsilateral eye, the contralateral eye is monitoring for threats, and that hemisphere is awake. So like the right hemisphere is awake and the left eye is monitoring for threats, while the left hemisphere is asleep and the right eye is closed, and then vice versa. So slow wave sleep seems to be helpful for rest, but sleep seems to be primarily related to resting the brain and not the body. And only cognitive functions really appear affected. So when you're sleep deprived, your physical functions don't seem to be very strongly impacted, nearly to the extent that your cognitive functions are. And consistent with that, there's a relatively weak association between your level of physical activity and how well you sleep. Also consistent with this is that there's an inverse relationship between active waking structural activity and delta patterns during sleep. So the most active parts of the brain during waking are also the most asleep during slow wave sleep. And so it seems that slow wave sleep is helpful for helping the brain rest. In contrast, REM sleep seems to do something different because the brain's actually quite active during REM sleep, and it seems to be related to cognitive reorganization. REM sleep's highly active, it's not there for rest, and interestingly, as you sleep deprive, you need more and more REM sleep. More and more of the sleep you get is devoted to REM. So REM seems to be more correlated with neural development. So animals that are well developed at birth have less REM sleep. Children of humans have relatively poor brain development at birth. They have lots of REM sleep, and that REM sleep tapers down over the course of childhood. And it has